Welcome, hackers, to the NASA Space Apps Hackathon. I'm Will Roberts, a data science evangelist at IBM. This video is a brief demonstration to show you how to use IBM products for machine learning modeling in the hackathon. You're going to be occupied solving the Earth's challenges, so you shouldn't have to worry over your tech stack. We have some amazing tools for you to try out, and there's a suite of machine learning products and services to make building your apps easy. To look at that catalog more closely, let me bring in Upkar Litter. Upkar?
Thanks, Will. Let's look at some of the services you can use on IBM Cloud for this hackathon. All amazing projects start with data. You need to collect this data and store it somewhere. You can use relational databases like Postgres and DB2 on IBM Cloud, but you can also spin up NoSQL databases in no time. You can use IBM Cloud to construct complex geospatial queries and also use visualizations powered by Mapbox. We also offer cloud object storage to store large unstructured datasets. We at IBM endorse and promote open source solutions. You can build, deploy, and manage machine learning models built on open source solutions like Keras, PyTorch, and TensorFlow on IBM Cloud using services like Watson Studio and Watson Machine Learning. You can also run Jupyter Notebooks and R scripts at scale on IBM Cloud. If you don't want to build a model from scratch, you can use one of the many pre-built models, including natural language processing, natural language understanding, visual recognition, Watson Assistant that can be used to build chatbots and conversations. These pre-built models are a great starting point, but you can also train them on your data. If you prefer low-code or no-code solutions, we have you covered with Node-RED. Let's look at some of these examples and resources you can use in a little more detail.
Hello, I am Jason from IBM Research. In this section, I will cover how you can leverage IBM Cloud to quickly get started with space app challenges. We know you all come from different backgrounds, and a lot of you come from other industrials that you want to bring your creative and novel ideas to help the challenge. However, if you're not coming from this domain, you may find it a little bit hard to get started, especially when dealing with satellite imagery data. For example, if you are a data scientist who experts in great machine learning techniques, you may find the raw satellite data format is not animated correctly, and the volume can also be so large that you cannot process in your own environment. Or if you're a deep learning researcher who wants to bring in your novel deep learning model, you may have a hard time figuring out how to pre-process and transform the satellite data into a desired array format. Here, we want you to spend your talent on the real creative and challenging parts instead of being stuck on this. So we present this section to you, which hopefully could get you easily started by showing you a series of quick tutorials, from how to pre-process and ingest your data, to how to leverage our cloud capabilities to help your machine learning or AI tasks in this challenge with IBM Cloud. Now let's get started. The first tutorial I would like to share is data pre-processing and ingestion. Satellite data typically come in different formats from different providers. Also, different data products are using different spatial reference systems with different spatial resolutions. All this might be a big headache if you are not familiar with this domain. That's why we present this tutorial for you, which hopefully could help you get rid of this headache. Here, we build an application that you can leverage as a template to process any satellite data into a unified ideal format for consumption. This solution is based on IBM Cloud Code Engine, which is a serverless Kubernetes-based solution. But you don't need to worry about learning this product, as it hides all the computation details for you, and we also make the template easy to configure, so you can spend minimal amount of efforts in making it work for your data. So no matter you are processing only a few times or processing huge amount of images, it can handle all this. Here, I won't go into too much detail about how to leverage this template, as we have all the implementation details in this tutorial. But I do want to share what kind of outputs are being generated from this pipeline, which in the later tutorial, we will show you how you could easily consume them as an analytical ready format. So basically, each image will go through two processing paths and generate two different forms of output. The first one is the raster path, which generates cloud-optimized GeoTIFF data, which you could easily query any image layer at any time step in any region, all in sub-second level performance, no matter how much underlying data you have. We will cover more in the next tutorial. The second path is the vector path. We know everyone loves data frame, So we also generate the data frame format for you from the satellite data by extracting the coordinates and values from the satellite imagery data. With this output, you can easily read it as either Pandas data frame or Spark data frame, and apply your favorite machine learning or AI model on top of it. We will cover more on this in the third tutorial. Okay, now let's go to the second tutorial, which is the raster data query that we just mentioned. This time, let's go to the demo notebook directly. So here, we assume you have pre-processed your data from the first tutorial, and in this case, we have processed 10 years global data from models. We do this because we want to show you even you have a huge volume of data, you can still achieve great performance when you query arbitrary data of interest. And we also made the API extremely easy to use. Let's look at these examples. So here is a basic example of query any layer at any time in any region. As you can see, all you need to set is the product name, layer name, date, bounding box of the region, and your out file name. Then you can just run the query function to get the data you want. We have a couple more examples here where you could use more than the basic bounding box. For example, if you are interested in the neighbor of a certain location of interest, you can use a radius search. We also support arbitrary geometry search. Here you could import any geometry of interest, for example, a polygon of interest. One thing we want to point out is that this query is not only fast, but also lightweight and horizontally scaled. In the example we showed previously, we query only a single node, but in practice, we will be more interested in pulling a batch of images, for example, a time series of satellite. And instead of stacking them sequentially, we can easily parallelize the data pooling either with a multi-node cluster or a single node with multiple cores, like what we are showing here. Finally, let's talk a little bit about the use cases. We really want to leave this fun part to you, but we think it can be helpful to give you some basic ideas. The first use case is data visualization. Being able to visualize data during preliminary step before any analytics is crucial. You want to visualize your data to get some impressions before jumping into your model directly. Another use case, which is my personal favorite, is to leverage our raster data query to prepare input data for deep learning models. Since each image are naturally a 2D or 3D array, you could use this demo to pull a time series of satellites into a 3D or 4D array, and use sliding window to get a batch of sub-arrays as your input for your deep learning model. We actually leveraged this a little while back and performed a deep learning-based change detection, and we found a change anomaly as shown here, which happens to be the 2018 slave fire that happened in California. We hope you could have more fun like this, and that's about this tutorial for querying raster project. Now let's move on to the next tutorial. We just showed you how to query rastering, which is essentially pulling images. If you remember, during our ingestion period, we output not only images, but also data frames. And that's what this tutorial for. For this part, we have a very detailed blog article. And I will skip the reading parts during this session, and focus more on the demo part. Please note that you could have a million ways of manipulating the vector data, because it is in your favorite data frame format. And what I'm going to show you is only one example, which hopefully you can leverage some components as building blocks of your analysis. Now, let's walk through the demo. This time, we want to leverage two different layers from water instant product and compute a derived water boundary. And we want to further apply machine learning on that layer to get the real water boundary. During the first step, we align and join two different layers. This is the water interpretation layer, and this is the mask layer. And we get a derived layer, which is the binary mask of water existence. From here, you could already see the obvious lake boundary that we are interested in. However, this is not good enough, as you can see there are still a lot of noises. So during the second step, we apply machine learning on the derived layer. Here, we use dbScan clustering to cluster the points and remove non-cluster points, which are essentially the noises. And we get back this, which is quite a good water binary mask, but we can do even more. So far, even we get a good visualization of water, but remember, this is is still either an image or a data frame, where it is still just a bunch of coordinates. And typically, we are really interested in the real boundary. So in the final step, we apply our spatial temporal toolkit, which is available in IBM Cloud, to extract the real boundary. Here, what we are showing is the convex hull of the boundary, which is the convex boundary of water vapor. You can also apply other functions like alpha shape to get the compact concave boundary, which would look like the middle one here. In fact, from here, you can do even more. You can apply a further step by applying a time series of such boundary detection, which can give you the idea of how lake boundary is changing over the years. This can be very helpful in the study of water shrinkage in certain regions. We really hope you could get more chances reading this tutorial yourself, as a lot of details are not covered in this session, but we are documented in this book. And this is not a case study, but also a set of building blocks that you can leverage for satellite vector data analysis in general. For example, in this first section, we have this spatial temporal layer alignment, which you can use on any layers when you want to align or join multiple layers that are not naturally aligned. And this is exclusive to our spatial temporal EF support that we import on IBM Cloud. Similarly, in the third step, here, we hope you could learn how to leverage IBM Cloud's native spatial temporal support to further analyze your data. And we actually have a link here, which you could explore much more functionalities that we support. So here is about the third tutorial, which is on query vector data. We hope you enjoy this. Now we come to the last tutorial. In this tutorial, we want to talk a little bit on the time series analysis. So far, we have been mainly focused on how to analyze satellite data as an image, as well as how to analyze the spatial dimension on satellite data. However, the temporal dimension is just as important as the spatial dimension. So in this last tutorial, we want to show you how you could perform time series analysis on satellite data, especially how to compare and generate temporal features, which can be very helpful for your machine learning and AI models. On IBM Cloud, we have native time series support, just as the spatial support we showed in the previous tutorial. Now let's go from there. With built-in time series functionality on IBM Cloud, you could perform various time series analysis on satellite data. I won't walk through every functionality here, but for example, you could leverage our season selector to transform a series of satellite data and decompose them into trim and seasonality. This is just as what you typically could do for a typical time series, but we have it naturally supported in IBM Cloud with many benefits. And one of that is the natural spark detection. For satellite data analysis, volume is typically much higher than other datasets, and data are typically distributed and being consumed as spark data frame instead of endlessly. So being able to perform various of time series analysis on distributed data can be a challenging task, but we get you covered as what we just showed. And with the generated features, you can either use our IBM Cloud Auto AI to build model automation, which will choose the best model for you from all various models, or you can also bring in your own favorite. That's about this tutorial, and that's about the whole tutorial section. We hope with IBM Cloud's native support on all of this, you can leverage our tools and templates to help with your work. And good luck with the challenge.
Hi, my name is Jeremy Nilmeyer. I'm a data scientist and developer advocate at the IBM Center for Open Source Data and AI Technologies. And I wanted to talk a little bit today about Watson Studio, which we like to think of as the portal to open source that is also powered by open source. As a member of the Center for Open Source Data and AI Technologies, Code aims to make open source AI solutions dramatically easier to create, deploy, and manage in the enterprise. And this is because we've been contributors to open source for pretty much since the idea of open source was created back when we created the Linux Technology Center. We're founding members of the Apache Software Foundation, Linux Foundation, and committers we have on the order of about 200, contributing to about 80 or so projects in the open source ecosystem. So we've got a proud heritage in open source that we do like to talk about when people are interested. In addition to our contribution to open source, we also provide tools for people interested in learning deep learning and the state of the art. So we have this thing called the Model Asset Exchange, which is basically a collection of Docker images that allows you to run pre-trained deep learning models that will do sort of various standard tasks. For example, identifying objects, classifying scenes, generating captions, generating audio samples, and we're constantly updating these. Just take a look at it, give yourself a little bit of time, and you can probably find something that does something that you need to do. Alternatively, we have some standard Watson APIs for things like speech-to-text conversion and some other ones. We also have, if you want to have your own custom-trained model, we have something called Watson Machine Learning, which is this API that will spin up a GPU instance that will allow you to train your own custom model. And it generates this kind of ephemeral GPU instance, so it's a little bit more easy to use in terms of resources. And if you want to do sort of exploratory deep learning on GPU resources, we also have a Watson Studio instance that connects to a GPU instance. So we also have a book, if you'd like to download that. This book really covers this sort of three-pronged approach to what really the state-of-the-art the open source deep learning and machine learning ecosystem is, and that's really, you've got deep learning, distributed computing and machine learning, big data, something that you need to run on a cluster that's going to be Apache Spark. You've got GPU accelerated deep learning, something that needs to happen on a GPU, that's probably TensorFlow, maybe PyTorch, or some of the other frameworks. Anything you can access through a Python API, and then you have the notebook, which sort of ties it all together. This notebook is this UI, common UI that accesses all kinds of different hardware environments. So you've got this nice, comfortable UI that you're familiar with, but you, under the covers, you can access a whole host of hardware environments. So I just want to walk you through just very quickly what a Watson Studio instance looks like. It looks a whole lot like a Jupyter notebook. In fact, it is built on Jupyter. It's just now it's running on a cloud instance rather than on your local laptop. So as soon as your data starts to get large or your workload starts to get large, the scalability is built into it, and you can already have it running on the cloud. So this here is a PySpark notebook. So you've got, if you look here, if you want to see what the Spark context is, it brings up the Spark context. Now here, if you go to this information tab, it'll tell you what your environment is. So you can define various environments. So here you have a Python and Spark environment. You can run R, you can run just vanilla Python with no Spark, you can run Scala and Spark. Additionally, you can create a GPU accelerated notebook and run, you can also run TensorFlow on just standard GPUs or standard CPUs without the hardware acceleration. So come back to this, and this is just walking you through what it's like to set up your hardware environment. You've got default Spark and GPU, pick your hardware configuration, number of CPUs you want to have, and the language that you want to run it on. So here's a QR code and a link for the book if you want to download that, and thank you for your time, and good luck. Can't wait to see the projects.
Thanks, guys. We from IBM are grateful that you are here to help us try and tackle the world's problems. If you have any questions about how to best accomplish your goals, come and find us in Rocket Chat. Look for the users with IBM in their username. Happy hacking, everyone, and we look forward to talking to you soon.